let's take a likely JAMB question to what we just studied. We have a question on the board. The representation below contravenes which law? The representation below contravenes which law? We have 1s2, 2s2, 2p6. The representation below contravenes which law? Okay, we have a likeliest JAMB question on the board. The question says the representation below contravenes which law? We have A, Hund's rule. We have B, Pauli's principle. We have C, Abba's principle. We have D, Le Chatelier's principle. Look at this question on the board. Very simple. Very simple to answer. The question says the representation below contravenes which law? First of all, you tell yourself which element is having this representation. This representation has 6 electrons. So the element in the periodic table that has the atomic number 6 is carbon. If the atomic number of carbon is 6, it simply means the electron number is equally 6. But how do you represent or feed these electrons in atomic orbitals? Mind you, we just studied modern way of learning electronic configuration, and again I gave you 3 laws or rules or principles that enables us to feed electrons in orbitals with ease. Looking at this question, you can simply agree with me that the law that has been contravened or disobeyed or what or defied is Hund's rule. According to Hund's rule states that, as studied earlier on, that electrons are fed in orbitals singly first before pairing takes place in a degenerate orbital. This 2p2 orbital is a degenerate orbital because it's having what? 3 subshares, and each of these shares are sharing the same energy level. What do you mean by sharing the same energy level? Look at it. They are together. So it simply means they possess or they share the same energy level. But they are what? Subshares enclosed in a particular orbital. So you must obey Hund's rule when filling electrons in such degenerate orbital. Degenerate orbital. The 2p and 3d orbitals, both of them are what? Degenerate orbitals. So when you are filling electrons, you feed them singly first before pairing, as we have it on the board. But if you do it in this manner, this is wrong. So the right thing would have been singly first before pairing takes place in a degenerate orbital. One other question JAMB we always ask is, having known how to write electronic configuration and having known how to show the representation, they will still proceed to ask you how many unpaired electrons does the atom of element called aluminium has. We'll use aluminium as a case study to answer this particular question. Again, what you are expected to know under this topic is the number of unpaired electrons that every element has or possesses. Number of unpaired electrons. We'll use aluminium as a case study. Unpaired electrons. We want to look at how we determine the number of unpaired electrons in an atom of an element. We'll be using aluminium as a case study. Aluminium has the symbol Al. Like I said earlier on, the first thing you should do is to identify the atomic number of the element that you want to determine the electronic configuration and also the number of unpaired electrons. Aluminium has atomic number 13. The atomic number of aluminium is 13. So it simply means it equally has 13 electrons. 13 what? Electrons. So let's first of all give the electronic configuration of aluminium. From what I have taught you earlier on, we have 1s2, 2s2, 2p6, 3s2, and 3p1. Let's sum up the powers to ensure that we have not exceeded 13 electrons. We have 2 plus 2, 4, plus 6, 10, plus 2, 12, then plus 1, 13. 1s2, 2s2, 2p6, 3s2, and 3p1. For you to successfully determine or with ease the number of unpaired electrons, you must show the diagrammatical representation or the filling of these electrons in their respective orbital. Did you get what I just said? I said for you to be able to determine the number of unpaired electrons in an atom of an element, you must show the diagrammatical representation of these electrons in their respective orbital. Let's begin with 1s2. We have 1s2. Of course, this is not a degenerate orbital because it's not having subshare. Now, you have to apply Pauli's exclusion principle. Do not put more than 2 electrons into the same orbital, but with opposite spin. Then we have, of course, for the 2s2, how do you feel? Do not put more than 2 electrons into the same orbital, but with opposite spin. Then, of course, the 2p6 is a degenerate orbital because it's having 3 subshare. And as such, you must apply both Pauli's exclusion principle and Horn's rule, most especially Horn's rule. So electrons are fed into orbitals singly first before pairing takes place. Singly first before pairing takes place in a degenerate orbital. In a degenerate what? Orbital. Then of course we have the what? We have the 3s. We have 3s2. Of course, do not put more than 2 electrons into the same orbital, but with opposite spin. And of course, we have the what? The 3p1. It has 3 subshares. So this is a what? The degenerate orbital as well. Fill it singly first before pairing. Of course, it has just 1 electron, the 3p. And so this is how you fill it. If they ask you how many unpaired electrons does this atom of element called chlorine have? The answer is what? 1. The 1 is not this one that you have written. They said how many unpaired. We only have one place that is not paired. Here is unpaired. So they ought to have been an electron here. So the electron that is not here is the one that is what? Is the one that would have been the paired electron. So this one is an electron. They say how many unpaired? We have just 1 unpaired. This is 1 electron. Nothing is being paired to it, like there is no other electron that is attached to it. So that's why we say aluminum has 1 unpaired electron. This one is not paired. So this is the electron that is not paired. Let's assume that we have an element. Let's take any element X, for example. X represents an element. Let me say here we have 2 electrons. How do you apply these 2 electrons for an element X whose 3p orbital is having 2 electrons? You simply obey Horn's rule, singly first before pairing. And of course, if you are asked how many unpaired electron is present in this element, the answer would have been what? 2. 1, 2. Let's assume again that you have another element X that is having 3 electrons in its 3p orbital. You obey Horn's rule by applying them singly first. If you are asked how many unpaired electron has an atom of an element with the 3p orbital having 3 electrons, the answer would have been 3 unpaired electrons. If I increase this now to 4 again, let's assume that an element has its 3p orbital occupying 4 electrons. You now fill it singly first, 1, 2, 3, before pairing. How many unpaired electrons is present in this particular element? The answer is 2. 1, 2. This is not paired and this is not paired. So that's the simple way of determining number of unpaired electrons in an atom of an element. Once again, my name is Mr. Michael Osai, your chemistry instructor. But I want you to do well to subscribe to our YouTube channel for more of this. But before we go for the day, a quick recap of what we studied this morning. What we studied this morning was all about modern way of writing electronic configuration by making use of the various block of elements or atomic orbitals. And what we studied, I said we have 4 atomic orbitals or blocks of element. And from there, I told you that each of these orbitals have their respective maximum number of electrons that they can take or occupy. I studied earlier on as well, the x orbital can take a maximum of 2 electrons, the p orbital a maximum of 6 electrons, the d orbital 10, and of course the f orbital a maximum of 14 electrons. And we look at examples of elements and the various ways of writing their electronic configuration, making use of these 4 blocks of elements. And finally, from there, I equally showed you how to determine the number of unpaired electrons, making use of 3 laws or rules or principles guiding the filling of electrons in orbitals. We saw what Pauli told us about the filling of electrons. We equally saw what Alba told us about the filling of electrons. And finally, Bond's rule of maximum multiplicity is true in diagrammatically representing electrons in atomic orbitals. See you next time.